Okay, so we looked at flow visualization as part of kinematics, and we encountered two ideas, one being streamlines and the other being path lines. So as we learned through various example problems and also to some degree of intuition, that streamlines actually give us an instantaneous snapshot of what the flow field look like. So if I draw a set of streamlines, I'm just drawing something which has a little weird shape. What you see from these streamlines is what the flow field actually looks like. So if you have a streamline which kind of has this kind of a tortuosity or bend, you also get a feel for what the flow would actually look like in that particular region. And one key idea of streamlines is that since streamlines are curves on which the tangent gives us the velocity vector, streamlines cannot intersect. If two streamlines were to intersect, then you would have at the point of intersection an indefiniteness regarding what the tangent is. There is one exception, and that exception is something that we have already seen in a problem that we worked out in the previous lecture, that if you have a velocity field of this particular form, the streamlines are rectangular hyperbolas because the equation for the streamlines turned out to be x1, x2 is equal to constant. And if you remember from the discussion from that lecture, I mentioned that if that constant were to take a value of 0, then the x1 axis and the x2 axis are also streamlines, and they do intersect. That's not something that is a surprise because the two axes would intersect at the origin. So does that violate the statement which I just said, that streamlines cannot intersect? So streamline cannot intersect is based on a physical ground that at the point of intersection you would have the velocity vector be indeterminate, because how do you draw two tangents at the same point? The exception being if at the point of intersection velocity goes to 0. So the intersection of streamlines would occur at points where velocity vanishes. By velocity I mean all components of velocity. So the entire velocity vector vanishes at those points, and those points are also known as stagnation point. So you can have intersection of streamlines occurring at locations where the entire velocity field goes to 0 at that particular point. So then there is no complication regarding how do you draw the tangent. So this is what we learned regarding streamlines. We saw that how streamlines actually give us this instantaneous snapshot of how the fluid is actually moving. And we also saw the example of there being path lines which required us to actually say that given a particle that starts off from some initial location, what would be the trajectory as it moves under the action of this velocity field. So what we solved, if I put a label P to say that I am solving for the coordinate, so we integrated these equations to find what the trajectory of a fluid particle is. So the streamline information gives us the velocity field description everywhere in the flow at a given instant of time. The path line information gives us the trajectory of a fluid particle that is starting from a particular point. And obviously, if the flow is steady, a path line would coincide with a particular streamline. So a path line which starts at a particular point on that streamline will stay on that streamline forever. There could be one more way of visualizing it. So for instance, I mean, if you were to think that where do you see streamlines? So if you were looking at a weather map, let's say one example where I'm drawing a crude example of the southern part of the country, and if you go back, the very nice places where you can check. One popular place where you can always check the wind speed instantaneously is this website called Windy. So if you open Windy on your phone or on your computer, you would actually see that at this instant, what does the wind vectors look like, and typically this would be at a given height in the atmosphere. So what are the directions of the wind at a particular location? So this gives you an instantaneous wind field pattern. So in some sense, what you are looking at is the streamline pattern at a given height from the surface of, from the land surface. You obviously can do this by, if you have a flowing river and or a pond, and you sprinkle some sawdust on the surface of the water, you would see that the sawdust is going to go and clump and move around, giving you a feel for what the velocity field is. So for instance, if you see the sawdust going around in a circular motion, that means it has gotten trapped into a flow field where things are moving around in circles. Else, if you were to actually just track an individual sawdust and see how it moves, then you are tracking a path line. Now, you could ask a different question. Let's say I continuously keep adding sawdust at a particular location. So I mark this point as, let's say, Q. So there is continuously sawdust that is being added on the surface of water. You are dropping sawdust constantly at a given point. And each of these dust particles, which are significantly light and can float, they get drifted by the river. So there is a river and the stream is flowing, let's say, towards the top right corner. As you keep dropping these dust particles at a particular location in river, it is going to trace out a trajectory. Now, if the flow was steady, then every time you put a particle here, it's going to always faithfully follow the trajectory that its predecessor has followed, which is the streamline. The flow is steady, there is no change in the streamline pattern. So the moment you drop a particle exactly on a streamline, or rather when you drop it, it will stay on the streamline where it has landed. So if you are releasing exactly at the same point and if the flow was steady, there is no reason for it to deviate from what its ancestors, so as to say, was following. It will exactly remain on that track. The situation becomes more complicated if you have a time dependence in the flow. So again, going to the example that we are looking at, let's say the river stream that is flowing, and you are thinking of what would happen to the dust particle. So at t equals 0, you have released a particle, or rather not t equals 0, but a long time earlier. So let's try to count this. So at a time instant, let's start with 0 itself. So at time instant 0, you release a particle and then you stop your clock at 10 units and see where this dust particle lands. At time equals t equals 1, you release another particle exactly at the same location. So at 1 unit later, you have released one more particle. Now, because the flow is unsteady, the flow that this particle experiences is not guaranteed to be the same as experienced by the previous particle. So what it would do, it would move around, and by the 10th second, it might take a different route and land up in a different location. And you can continuously keep repeating this process. You can release something at t equals 2, it can go somewhere else, it can do it at t equals 5, and then you could probably release something at t equals 8, and then eventually there is a particle which you are just about to release at t equals 10. So all of them are not necessarily going to follow the same trajectory and thus will not necessarily be at the same location. So now if you were to connect this line, that I'm drawing a line that connects all these points. So I'm doing this in a smooth manner. I get something like this. This green line that I've drawn, it basically connects where each of these particles are located, given that between the time interval 0 and 10, I've constantly been releasing these particles. So this is something that you observe. One of the best examples is when you have an incense stick, an agarbatti. So when an incense stick is burning, you are releasing the soot or smoke particle at the tip of that incense stick. And assuming that it has not burnt enough, the height at which you are releasing it is more or less the same. So you are going to see this nice smoke plume that is rising on top. So what you are seeing here are dust particles that have come out of that agarbatti and but at different instants in the past. What you are observing right now is the instantaneous position of various smoke particles that have been burnt and ejected from that burning tip at different instants in the past since it started burning. The same thing you would observe in a chimney. When you are looking at a chimney and there is smoke billowing out of that chimney, what you are observing is something that has something burnt and immediately released into the external environment, and far ahead in that smoke plume that has come out, whatever is at the tip has probably come out much earlier. So this is a description where you are looking at the final position of particles that have been released from the same location but at different instants in time. Their initial position is the same, but they are releasing or they're leaving that initial position at different instants of time. Another way of saying this is at t equals 0, consider particles that start off from different initial positions. Okay, so they are, one of the particle is starting off from, let's say, coordinate x with superscript 1, superscript 3, superscript 4. Each of these particles at the time instant t0, they start off from different points in space. Then as you march forward, they all pass through a common point which I have chosen, but they are not guaranteed to pass through that common point at the same instant in time, right? They are starting from arbitrary points in space as initial condition, let's say together. So which means that for them to arrive at a common terminus will not happen at the same instant in time. So this is a different way of saying what I just said earlier. Earlier I said they are all released from the same point but at different instants of time. Now if you were to think of taking time further back in time, then they were starting off at the same instant at different location and come and congregate at one single point, but it is not truly a congregation because they are arriving there at different instants of time. Which means if you were to march forward and say, so this was at t equals 0, so x4 arrives here at time interval t equals t4. x3 arrives here at time interval t equals t3, x2 arrives here at time interval t equals t2, and x1 arrives here at time interval t equals t1. Now let's say your clock stops at the time interval t equals to capital T, which means where it is going to be located is obviously again going to be a very different point. And now if you connect this, you are going to get a curve, right? So this gives us a picture which is known as streak lines. It's quite easy to visualize because if you think of examples like an incense stick or a chimney, it's quite easy. But if you have to solve for it, it is a little tricky. It requires how we have done the path line calculation. And again, it goes without saying that if you had a problem which was steady, then a particle being released at a given point, even at later instants in time, will faithfully stay on that streamline. Which means streak lines, streamlines and path lines will coincide for a steady velocity field. So we'll take the unsteady problem that we have solved. u1 is equal to x1 by 1 plus t, u2 is equal to x2. So we solved the path line equations. So the path line equation gave us x1, 1 plus t, which gave us x1 of t was x1 of 0, 1 plus t. This was the solution, that if it were to start off from some initial position, and just to, because we are going to introduce now 2 points, the initial point at t equals 0 and the common point through which they pass. So, I am going to call the initial point as A1, A2, A3. So, my streak line calculation is, what does the curve look like for the points which pass through y1, y2, y3 over a time interval that goes from 0 to, let us say, some capital T. How does it look like? Or in that time interval between 0 and t, how does it actually the streak line look like for all points that have passed through the point in space which is given by the coordinate y1, y2, y3. So, when I solve the path line equation for a point that was at A1 and A2 at t equals 0, this is what we got, right? When we integrate the x2 equation, dx2 dt is equal to x2. So, it has a solution that at t equals 0, if it was at the point A2, then x2 of t is A2 times exponential of t. This is from our path line calculation. Nothing new we have not done anything new yet. Okay. Now, what we are saying is that at some time interval, which is between the final time instant t and the time instant 0, it passes through the point y1, y2. I am just doing 2D right now. Again, the algebra can be extended to 3D. So, you understand conceptually what you are doing. You have said that the position of a fluid particle which was at the location A1 and A2 at t equals 0 is given by this path line equation. Now, A1, A2 is not something that we are interested in. The problem statement is, what is the streak line for fluid particles that pass through the point y1, y2 at different instants between t equals 0 and the current time t. That is the thing that we are interested in. We are interested in that curve. But when we calculated it in terms of everything that starts off at t equals 0, this is what we get as the path line equation. So, now we need to phrase this saying, all the fluid particles that start off at time t equals 0 from point A1 and A2, they are going to cross y1 and y2 at different instants in time, which is between the window 0 and t. So, if we work this out with these path line equations, at t equals s, x1 is equal to y1, at t equals s, x2 is equal to y2, right? What this does, it tells me that my initial coordinate is related to the coordinate of interest with this relation. You see what we have done here? A1 and A2 was nowhere there in the picture. Where I was at t equals 0 is not something that I actually gave in the problem. The problem said, I am at the point y1, y2. Particles are passing through this point at 0, 1, all the way till t. So, s is that variable which is spanning this entire range. You have fixed t. You have said that, let us say, the clock runs between 0 and 10 seconds. So, s is a variable that takes between 0 and 10. So, what this tells us that the fluid particle would have been at points A1 and A2 if they are going to pass through y1 and y2 at an instant which is s that lies between 0 and 10. So, if you choose s as 5, you can put s as 5 and you will get A1 is equal to y1 by 6. If you put s equals to, so let us put s equals to 0, A1 is equal to y1. What does that mean? It means a particle which was released at t equals 0 from the point y1, obviously for that the initial condition a1 is also equal to y1. For a particle which was released at s equals 1, or not released, but it passed through that point, because I am now saying that it is passing through that point y1, its initial condition is y1 by 2. So you are defining initial condition as a time instant t equals 0. If I am expected to pass through a point at some time interval between 0 and t, obviously that point is going to be different from where I was at t equals 0. And that is exactly what we are trying to work out. So with this, now we have a relation of the initial condition, and we are almost done. We have this gives me my equation for streak line. So what do you need to do? You need to choose a value of s that runs between 0 and t, and you will get the curve. So you have fixed the value of t. You have said I want to find out the streak line at a time instant t. Once you have fixed that t, then the streak line equation, once t has been fixed, now I can try seeing if I can eliminate s. So here I have, so let's use the x1 equation. So I have 1 plus s is y1 by x1, 1 plus t, or s is y1 by s1, 1 plus t minus 1. So if you plug this into the expression for x2, you are going to get an expression of x2 is equal to y2 times some function of y1 by x1 and t. So once you fix your t, you say at an instant, let's say 10 seconds, what was the equation for streak line that started off from the point y1, y2? This is what the curve will actually be. And you can see with the expression that you have, it has no resemblance to what was your path line equation, no resemblance to what was your streamline equation. So the three are going to be in general completely different if the flow was unsteady. But this is what conceptually it means. The last bit, which is also going to actually take us to the next topic, or the next thing that we are going to do in terms of visualization, is we have been talking about tracking individual fluid particle. Let's now think of fluid particle being released simultaneously in time, but at different locations in space. So what I have done here, I have drawn a line. Now you can draw a line in a fluid. You can take a dye which doesn't diffuse very quickly in the fluid, and you draw a line in that fluid. Once you draw a line in that fluid, then you are going to actually observe that as the flow evolves, this dye is going to change. It can do all kinds of different things. So this is at t equals 0, t equals t1, t equals t2, t equals t3. So that single line, as you observe it in time, it can obviously translate. So if you put a stick in a fluid, consider a stick which is massless. So what the stick does, it basically just responds to the flow. So every point in the stick is moving with the velocity at that location. Now if the stick was rigid, then what would happen to the stick? The stick can just do a translation. The stick can also do a translation coupled with rotation. So a rigid body basically will have a translatory motion and a rigid body rotation motion. That is what will happen in a stick. But a line that I have drawn in the fluid is not a rigid stick. So what you see through this is actually a measure of the deformation that is happening. So the line is not just translating, it is moved from its initial location. Certain segments of the line is also rotating, but there is also distortion that you see in the line. So this is known as a timeline. So if you have a timeline which in a flow gradually looks like this, as you observe it, the timeline is translating, but it gives you this kind of a shape. What this tells you is that the deformation in this part of the flow is negligible. The deformation in this part of the flow is actually quite strong. So visually, just looking at these kinematic observations that you have, you are actually starting to infer what is going on in the flow. You start to actually understand that yes, there are regions in the flow which is probably deforming more than the other. And goes again without saying that if you now were to track this, if you have a streamline, the timeline is going to deform even if you have a steady flow. The deformation of the timeline has no connection to whether the flow has a steady component or if the flow is unsteady. So it depends on how spatially the flow varies. So timeline is actually capturing, do you have a spatial variation of the flow? So that line segment distorting is actually capturing that spatial variations or gradients in the velocity field. So you learned 3 key ideas: streamline, path line, streak line, and timelines. The first 3 would be identical if you had a steady flow, but in general for an unsteady flow they can be quite different. So I'll share a set of videos which are actually very popular. They have been shot long back. I think it's National Center of Fluid Mechanics, NCFMF, I think. Fluid Mechanics videos, which are there. You can find them on YouTube. They have a beautiful flow visualization. I mean, they have it on entire thing on fluid mechanics, but the flow visualization videos, even though they have been shot quite a long time back, beautifully illustrates the difference between these for various kinds of problems. For instance, one problem that they have is if you have a flapping plate. So imagine that there is a pinned plate and the plate is undergoing oscillations. So when you have this flapping plate, the flow is unsteady. So you can start asking the question, what would the path line look like? If you release a fluid particle, what would the corresponding path line look like? So it would obviously, as the plate comes in, because there is the domain itself is switching. So what kind of a motion would happen for a fluid path line? You can ask, what is the velocity field? What does the velocity field look like? And for that, you need to freeze the frame. So what they will do, they will consider 2 very short time intervals of the motion of that plate. Very short time interval, because then you can actually, so what you can do is you can release a lot of fluid particles, and in that small delta t you find where do they get displaced, because that can then help you compute what is the velocity field. If you want to compute velocity field from an experiment, you want to see small displacements of these tracer particles. So you are looking at the motion, and in a small time interval you try to see that how do these things get displaced from its location, and their displacements would actually tell you what is the velocity field at that particular point. So you get a picture of streamlines, and then you can actually start releasing particles which are from the same point, and you would observe what would be connecting all of those dots. You would observe what would be the streak line. So it's quite nice in the sense of getting a feel for what's going on. So this is what we wanted to discuss regarding flow visualization, to understand how do we actually look at a flow and try to infer of what is going on. The streamline gives us a picture of the velocity field. The path line basically, in a sense, captures how individual particles or individual tracers are going to access different regions in the flow. Do they get trapped in some parts? Obviously, this becomes quite crucial when you're thinking of an unsteady phenomena, because otherwise you will have to look at a series of snapshots of streamlines. And finally, you have streak lines, which tells us that if you are constantly injecting tracer particles in the problem, because whenever I'm using the word particle here, I'm implying something that does not have its own inertia. So it's small enough that it doesn't disturb anything in the flow. It is just capturing or shadowing what the flow field looks like. So the timeline picture now takes us to the next part, trying to understand deformation in a flow. So when we are thinking of trying to understand deformation, I'll consider at a point x and another point which is x plus delta x. So there is a small displacement that I have of delta x. So now the velocity at point x is u of x comma t, and at the same instant the velocity in the neighboring location is u plus x delta x comma t. So if I want to find out what is the change in the velocity, by how much does the velocity actually change between these 2 points, if I'm trying to make a measure of that, then what I'll do is I'll do a Taylor series expansion, which will be in this form. So written in index notation, delta ui is going to be delta xj dou ui dou xj. So the velocity at the neighboring point, I can expand this u of x plus delta x comma t is u of x plus delta x dot del u, and then the term would be, the higher order term would be order delta x square. So what we have said now is that the difference of the two velocity as delta x becomes small can be approximated as delta x dot del u. So this is the difference of velocity between two infinitesimally separated point, that how much would the velocity be different. And this quantity dou ui dou xj, which we got introduced purely from a mathematical point of view earlier when we were learning about order 2 tensors, is the velocity gradient, and as it is an order 2 tensor, you can write it as a velocity gradient tensor. So as you can see that unlike the gradient of a scalar, so if you were to write down the gradient of a scalar, let's say temperature gradient will have 3 components: the variation of temperature along the direction x1, the variation of temperature along direction x2, the variation of temperature along direction x3. Whereas this quantity, the velocity gradient, has 9 components. It will denote velocity variations like velocity along the one direction of the one component, variation of the velocity along the one direction for the 2 component, variation of the velocity of the 3 direction along the one component. So you will have all the 9 components of this velocity gradient. Now the velocity gradient by itself obviously captures deformation, but we can make this a little further, we can simplify this a little further. Because we have learned when we studied order 2 tensors that any order 2 tensor can be written as a summation of a symmetric and an antisymmetric part. So in the case of velocity gradient, we can do the same exercise. We can write the velocity gradient in terms of a part that is symmetric and a part that is antisymmetric. So, the symmetric part is known as the rate of strain tensor and the antisymmetric part is known as the rotation tensor. So, we understood that there is a velocity gradient which captures how two neighboring points differ in terms of their velocities. So, it gives us a measure of the difference in the velocity, and that velocity gradient, which is trying to give us an information of deformation, can be split into a symmetric part and an antisymmetric part. And the symmetric and the antisymmetric part fundamentally have very different ways in which it deforms. And that's going to be what we will look at. So, first we are going to look at the symmetric part and then we will revisit the antisymmetric part. Now, if the tensor was symmetric, it's not going to have all 9 elements. So, if I were to write this out in its matrix form, I will have E11, E12, E13, E22, E33, and here I will have E23, and because this is a symmetric tensor, this is going to be E21, E31 and E32, or E31 is the same as 13, so this is 13 and this is 23. So, there are 6 elements of the rate of strain tensor. Whereas, if you do the same thing for the rotation tensor, that is an antisymmetric tensor, which means diagonal terms are going to be 0, and I will have R12, R13, R23 minus R12 minus R13 minus R23. So, the rotation tensor will only have 3 elements. So, the velocity gradient has, without any further information, has 9 elements, where the symmetric part will have 6 and the antisymmetric part will have 3. And we will see when we move to the antisymmetric part that this representation in terms of 3 starts to tell us that this could probably be written in terms of a vector, because it has only 3. So, in next class, we will actually start from understanding what the symmetric part does, what kind of a deformation does the symmetric part play a role in, and then once we learn about the symmetric part, we will then try to see that does the antisymmetric part play a role in deformation. Okay. So, I will stop here and I will take questions. Yeah, so E21 will be E12, you are right, they are equal. So, path line, so if you think in terms of this particular problem, right. So, if you do a path line for this problem, let us put a label for a particular point. So, the path line for that particular point may, sorry, it won't. This is what the path line will look, because you are tracking a particular point, right. Yes, which is given by a point. So, I am looking at its trajectory, whereas in a timeline, I am saying that if I have a set of fluid particles drawn out in some shape, I have taken a line here. So, that line, how does it move? Yeah. All the particles, where are they? So, a collection of particles They need not. So, I mean, an example which often I give in terms of viewing students in class as fluid particles. So, if you think in terms of path line, you track an individual particle. So, let's say the student enters from the class. So, Navneet has entered from the class from the door, and I constantly keep tracking him. Okay, very invasive, no privacy, but I'm basically tracking where he is. So he moves through the door, he comes through the forward from that row, maybe moves around and goes and sits there. That is the path line. Now, while all of you are entering the class, when the class is going on, you're doing your thing. You're moving around. You have not yet gone and sat down to your place. Now, if I just freeze the frame and do it like take two frames which are just almost next to each other, I will find out that in what direction are you moving. So that gives me that instantaneous velocity vector associated with each of you, right? Streak line would be all of you are entering through that door at different instants. All of you have not come into the class exactly starting at the same point. And then I say, okay, now where are you located? So I'm just, let's say the first person to enter was Himanshu. Okay, and I was the last person. So I draw a line which basically connects all of you and then comes back to me. So at a particular time frame, all of you have entered at different instants in the past. All of you have entered this class at different instants in the past. Door is the point through which all of you are entering. So there is a 1 point entry. But all of you are not entering exactly at the same instant of time. You are entering at different instants in time. So now if you were to draw a curve that joins all of you, here there are only a few of us, but theoretically if you had like the whole class being packed, in which case you can actually draw a very fine line connecting everyone who has entered sequentially. Then you would get a curve and that would be your streak line. And the timeline would be if, let's say that the 3 or 4 of you, maybe if you're sitting in a given line in a bench, you hold a rope with you, okay, and then you start walking. So obviously when you get up and start walking, everybody is not going to necessarily walk with the same speed. And if the rope was, for the sake of our argument, infinitely extensible, you are not constrained to move by the rope. So somebody moves out quicker, somebody is lagging behind a little bit, the other person decides to probably not move right now. So now if you think of the shape of the rope, which was like a straight rope, has now become a distorted rope. What that gives you is an information of the relative motion between each of you. That is what we are learning in terms of deformation. It is not just telling you how fast is one person moving. The motion of an individual is not going to give you any information regarding how much deformation is going on. The information regarding deformation comes in regarding how rapidly do you move with respect to your neighbors. That's the part which we are getting introduced through timeline, and then when we are thinking of deformation. That am I moving? So if all of you move very rapidly but at the same speed, then that's a rigid body motion. So the velocity, the exact magnitude of the velocity is not going to tell you any information regarding deformation. Deformation comes in when you're thinking in terms of relative motion. So this is basically the idea of what you have from each of these diagnostics. Other questions? Yes. Yes, so the streak line requires you to have everyone entering from or being introduced from the same point in space. If there was another door in the classroom through which students would be entering, they would have their corresponding streak line. But since this classroom has one single point of entry, there is one unique streak line that we can define. Each one of us have entered this classroom at different instants of time. So starting from the person who entered in the last instant. So let's say we stop the clock the moment we have the last person enter the room. So that person is from where we start drawing the line, because the moment that last person enters the room, he or she is going to be exactly at the door. They step in and we say stop. So now we start drawing a curve. The person previous to the last person is somewhere maybe closer to the door, not as far as here. and then we gradually try to track who all have entered sequentially, and you would get a curve. So that's just the example, the human analog of a burning incense stick, right? Like smoke particles coming in. The only difference is that your motion, the big difference or rather is your motion is self-generated. You are not moving due to anything else. There is no flow here. Even though I'm giving you an example to understand the kinematics and visualization, you are moving due to your own volition, due to your own willpower and your own, I mean, if you feel a little tired, your shoes are broken, then obviously that dictates how you move. But otherwise, there is nothing else that is trying to move you. So that's where there is a big difference in what fluid particles are doing and what you see in a collection of any moving entity. But the broad idea of visualization stays the same. That you can understand path lines, you can understand streamlines, you can understand streak lines, and you can also understand timelines by thinking in terms of how objects actually move around. And the timeline part is where you get a picture of what deformation is happening. You can also understand deformation from streamlines. So if you see streamlines are basically spreading out, if some degree of how the streamlines are spacing out, if there is a change in the streamline, but it is not as direct as the timeline picture. The timeline picture immediately tells you where you have deformation. If you start with a straight line, if the straight line all it does is, so you take this example. I have a straight line, the straight line keeps rotating. Now, if the straight line keeps rotating, but the length is preserved, then that is a rigid body motion. The straight line keeps rotating, but also elongating. Then that is rotation coupled with stretching. If the straight line rotates and does a bit of this, so there are also further fine scale deformation that is happening. So this is deforming, this is not deforming. So these two are deforming, but as you can see that in the scenario where it just stretches, there are no local distortions. You just have a line basically being stretched. It rotates and it gets stretched. And then in the second case, you can realize, so comparing the second and third, both are cases of deformation. But from the second and third, you can imagine that in the third case, there are spatial variations which are more local in nature. As you will, when we go through this exercise of deformation and velocity gradient, rate of strain tensor, you will see that a deformation where the line just gets stretched in this manner without any distortions is something that will be equivalent to the fact that the velocity gradient is the same everywhere in the flow. It's a constant velocity gradient. That's when you will get a picture like this.